Yay, we have 4 people. All right, let's start. Your truth 3 is basically making a cube, right? And then implementing a camera so you can move around the cube and see the cube from all sides. So first step, you make a cube, and I sent a link in the Discord for the link that we're using. So clone that repo if you haven't already, if you want to follow along. It just contains some extra function definition. So I just added these ones and also the static mesh class because I see he's writing all this code again. It shouldn't be that much. It shouldn't if we to write it again. But this is just extra stuff like for text chords, which we don't need. But if we ignore text chords, we could just leave that out. And the init function will ignore that as well. So if we run this and see what we get, just get a black string. You want to make a cube. So let's go to the cube. And in this function, let's, hold on one sec. All right. We define a static mesh class. So the basic usage of static mesh class is basically you define it like this, and then you can say what the positions are, which is just a vector of vectors. And you can say what the indices are, say what the colors are. So we want to define all of those. And then at the end, you just cube.init and return it. So that's the basic usage. And in the main function, all you have to do is just do cube.draw. And make sure like after your main function is ended, you cube.destroy. So that makes that frees any resources. I kind of moved away from making it non-copyable class because that was kind of annoying. So you have to manually destroy it. All right, so let's to define it. It's a little bit more involved than making a square, obviously. You have 8 vertices instead of 4, but there would be a lot more indices. So how many indices though? So let's think. We have 6 faces. Each face is 2 triangles. And remember in OpenGL, we render using triangles, not quads, because triangles, you can have a single normal, a single vector perpendicular to it. Whereas for a quad, you can have up to 2. So that's not good. So you have 12 triangles in total. And for each, we define the vertices, even if they repeat each other. So that's 36 indices. Now, if we were to not have any indices, and that means we have to have 36 times the size of each vertex, and the vertex could have the position, color, and text coordinates, which could take up a lot of space. But if we just to define the unique vertices, then that's okay. We can define the unique vertices and then define the 36 indices. That saves a lot of space. So let's do that. And I have this cube here. So I want you to imagine this cube. There's 2 ways to imagine it. You can probably see 0, 1, 2, 3, this face. Just imagine that as the one closest to us, because there are 2 ways to think about how I think it gets kind of trippy actually. And think of the 4, 5, 6, 7 face as the one behind. So we want to find the first face. To do that, we need 4 vertices, because that's the positions. And for each vertex, we can say, for the first vertex, we can say that's minus 1, 0, minus 1, 0, minus 1, 1, minus, no, 1. Okay, so let's think why this is the first vertex. So if you imagine the center of the cube as the origin, 0, 0, 0, then because this is our default coordinate frame and the arrows point in the direction of the positive axis direction, and So to go in the forwards towards us, towards out of the screen, we have to specify a positive z coordinate to go towards the direction of the first vertex. That's why it's 1. And of course, this will be -1 and 1, as we'd expect. Now let's do the rest of them. So we have, this is the front face. Okay. I'm just making sure I'm monitoring the Discord chat. So the front face, we have the second vertex here, the bottom one. So let's make sure we do that. And that's going to be -y. Now we can do the third one, which would be positive, and then last one would be both positive. Okay, so we can do that, but we've kind of hard-coded the width value. The width value now would be 2 units, but we've defined a width here. So let's actually find half the width to be width divided by 2. Replace each of these with HW. So that means the full width would be width, of course. HW. Sorry about the noise. There's probably a much easier way to do this. I just learned on Cleon, you could do Shift Alt and then click. So much better. Then the back face, which is exactly the same as the front face, except the Z coordinate would be -HW instead. Okay, and that should do it. That's all the unique vertices. To define the indices, let's do the indices first and then the colors. There are 36 of them. So these ones are a little harder to get right. The thing about indices is we have to define them in the correct winding order. And the winding order is basically if it's going counterclockwise or clockwise in the direction you specify the vertices. So if you look at this image, let me expand that. Your eyes here, you're looking at this cube. This cube here we see is 1, 2, 3. That's going counterclockwise. That's the winding order. And by default, the counterclockwise would be visible to you. And triangles that are clockwise are invisible to you. So we see that this one here, the one closest to the eye, is visible. The one further from the eye would be invisible. So essentially, all the outwards facing triangles would be counterclockwise if you view them from, like, okay, better way to explain is your eye, if you move your eye around, well, if you move yourself around the whole cube and you look at this triangle here, that becomes clockwise, counterclockwise. So then that becomes visible. That's how you can really think about this. So now we know how to define the indices here. And to do that, we look at the front face and we say, okay, the front face here is 0, 1, 2, 3. I want that to be visible to me from my perspective right now, from where I'm looking at it. So I want that to be counterclockwise. So to counterclockwise, I can do like, so this is the front. I can start from 0 and just go 0, 1, 2. That's the first triangle. And then say 2, 3, 0. That's 0, 1, 2, 2, 3, 0. 0, 1, 2, 3, 0. Yeah, so get the idea. So 1, 2, 2, 3, 0. We can do the back now. Now the back to, in our perspective, should be invisible. So that means we should do clockwise instead, so the opposite, so that it's invisible to us. It doesn't matter which vertex we start from. I just start from, I can say, start from 4. To go clockwise, do 4, 7, 6. 4, 7, 6, and the other one would be 6, 5, 4. And we could do the rest. So we have the top, and let me Yeah, so have a go at the top and the bottom. What you have to do, and the left and the right, so those are all the 6 faces. The top, we see that we want that to be visible. The bottom here, we want it to be invisible. Does that kind of makes sense, right? Because from our perspective, that should be invisible. And the left should be invisible because this face here should be invisible from our perspective, whereas the right here should be visible. I'm not sure. I will check your Medicare because you haven't finished your referral. So what do you think the top is? 374403 for the top. Yeah, so that should be visible. So that should be counterclockwise. So 3, 7, yeah, 3740. 374403. Yeah, that's good. I'll just copy that. All right. The bottom should let's just do it. So should be clockwise, so it's invisible. So 5, 6, 2, 2, 1, 5. The left is invisible, so that's clockwise. So that's 0, 4, 5, 5, 1, 0. Okay, and the right is visible to us. So counterclockwise. 3, 2, 6, 6, 7, 3. All right. That should do it, hopefully, if we haven't made a mistake. And the colors as well. So we don't want this to be just a big blob. We want to be able to see the side and know that that's the side. So we want some colors. We just need to define a color for each vertex. So there'll be 8 of them. 1, 0. Oh, let's initialize everything to 0 and just copy and paste that. So there's 4 for the front face, 4 for the back face, and then let's just define some random colors. So like 1 RGB. Let's do yellow to this. This. I'm just trying every combination, and probably have to repeat some here. But... Okay, so that's done, and we're returning the cube, and let's try to see what we get in the main. So all we have to do is define the cube, like I said. It's a static mesh. And then we have to say that's equal to make mesh, make cube, and let's make it a width of 1. And we draw it. That's it. Cube.draw. One other thing we're not doing is we have to use the shader. So I made a shader, and so we have to say gl use program, shader program, and make sure that's correct. So let's go to vert. All right, that takes in position and color. That's good. It passes the color along to the vertex to the fragment shader, and the fragment shader just uses the color as the frag color, which is linearly interpolated. So let's run that. Oh, not the bug. No. Uh-oh. I made a mistake, it looks like. Oh. Let's go to the cube. Oh no, this is a pain to debug. It might be the positions, so let's see. It would be the front face as well, so minus minus. Oh, here it is. These two are identical. It should be, this one should be minus. So that means I copied it here. and that should be minus. Okay, looking good now. But then a good question is, why is this a rectangle? Didn't we define a square? The answer lies in the main file. When we made this, because the viewport or something is rectangular. Yes, that's right. The viewport is rectangular. And so whatever's in NDC gets scaled to your viewport dimensions. That can be fixed using the projection matrix, which we will talk about later. Yep, so that's the cube. Let's work on the camera now. So what is a camera? Well, let me tell you that the camera doesn't actually exist in OpenGL. There is no camera, it's an illusion. So if we want to move the camera to the right, we're actually moving everything in the world to the left. So the camera doesn't really, the only information we need to store for the camera is its transformation. And then it's like if the transformation for the camera could be the translation, rotation, and scale of the camera. And then whatever we do to the world will be the opposite of those translation, rotation, and scale. In fact, it will be minus the translation. It'll be 1 over the scale. And it will be the transpose of the rotation. And then you multiply them in the reverse order that we normally do them. So we can do that. We can store that information in some camera structs that we have here, camera 2. But you'll find that it's easier just to store the position, so the translation, and the direction the camera is facing. And then we figure out the rest from that. So it's a little bit easier to work with if you do that instead. So all you have to do is define the position, glm vec3, in the camera.hpp. glm position is pos, and the direction the camera is facing, let's call it front. Point in front of the camera would be position plus front, because front is just a direction vector and position obviously is a position. Let's go to camera. So make camera should just initialize those values that I just, those variables that I just defined. So the position would be whatever I passed into this function, position. The target, so that's what we're looking at in the world. To get a vector from the camera to the target, that's the front vector, I have to do target minus the front position. But the thing is, if I want to move in that direction, in the front direction, if that vector I just created, target minus position, is like has a magnitude of like 2, then that means every step I take would be 2 units at a time versus just 1. So I make sure I need to normalize that so that the length of that is just 1. Okay, get view. Get view is the part where we define we get the inverse of the camera's translation. That's a bit involved mathematically. So let's just sidestep that for a second and think how our camera's inverse transformation will apply to each point in our world. Well, we'll just multiply the view matrix by the position. Let's call that U MVP. So MVP stands for model view projection. Let's make it a uniform variable, and so that's UMVP. It's a mat4, and then make sure we set it in the actual code. Where's the code? Where's the part? In the chicken lib. You'll find a function that helps get the uniform location of a uniform variable. So we pass it in the program, a shader program, and a name, so MVP. Let's call that GLUint. That's the MVP lock for location. We use the location to actually set the variable in the shader. GL uniform M matrix for FV. So that's how we set it. We pass in the location. So that's what we just found, MVP lock. The count of how many matrices I want to set, which is 1. Transpose, don't want to transpose. So GL false and fault value. So we can use GLM value pointer like we did last week. And what we pass in, we don't have anything to pass in just yet because we don't have the view matrix. So we just pass in the identity matrix. So let's go with mat4 1. And pray that works still. Yeah, that works still. So that's good. And then now we can define the view. So to get the view, right now, the only information we have is the camera's position and the direction it's facing. So there's an image here that I drew. This, you can imagine this bit here is your camera's coordinate frame. And the camera is looking at this ball. And we see that the Z vector is actually pointing in the opposite direction to where the camera is facing. That's kind of the default. And that makes sense because when we're loaded into the world, we're actually looking down the negative Z direction. So we have to create the matrix, the mat4, we have to calculate these vectors using cross products and the information we currently have. To do that, well, we know what the Z vector is already, because that's just the negative of the front, the negative of the cam up front. What's negative? Yeah, so let's call that Z. All right. Now we can figure out what the right axis is, this one here, and that will be X. Let's call that X. Right. How do we calculate X? Okay, so we have one vector so far. But for a cross product, we need 2 vectors to find the third vector that's orthogonal to both. That's kind of a problem. Does anyone have any idea what we do in this situation? If you've read Learn OpenGL, you will know. So the trick they use is we assume the camera is not tilted like sideways. So we can just take the up vector, so 0, 1, 0, that y-axis, default y-axis, and take cross product that with the direction, and then we can get the right axis. And that works because we're assuming that the camera is not tilted. Okay, but there is still a problem. Like, how do we know if taking the cross product between the up axis, this one here, and the direction here will result in this right axis or a left axis, if there exists one, but there's no such thing as one. We want the right axis. So we use the right hand rule. So if we imagine the thumb to be the cross product we want to calculate, so the thumb would be the right axis here. And then the A vector would have to be the up axis, and the B vector would have to be the direction. So that means I need to multiply the up with the direction in that order to get the right vector. So I can do GLM normalize, GLM cross to get the cross product. And inside, first I pass in the up. So up would be just 0, 1, 0. And the direction will be Z. Now that we have the Z and the X, we can calculate the Y. So actual y, not the fake one, not the one we use to calculate the x. That will be GLM cross of those. Now we have to use right-hand rule again. So we want to calculate the y-axis. So imagine the y-axis as the thumb, and then that would mean the direction would be the a vector, and the right axis would be the b. So it would be the direction times the right axis. So the direction is actually z, and the right axis is x, the one we just calculated. All right, now we have the three vectors. So we can define this mat4. So let's define a GLM mat4. And that mat4 would be, let's call it view. And then view, okay, remember, actually you probably, you may know this, but GLM's matrices are stored in column major order. Column major order means if you imagine a mat4's floats to be a contiguous array of values, then the first column of that matrix is actually stored as the first four values within that array. And then the next column would be stored as the next four values, and so on. So it'll be the x-axis, y-axis, and z-axis. So we can say the view's first column is equal to GLM vec4. Has to be GLM vec4. That's the x-axis. That's just x. And this is very neat, but I can just say vec4, pass in a vec3 as the first parameter, and then say 0 to make it a vec4. Cool. And do the same for the rest. That'll be the y. That'll be the z. Let's make sure it's an identity matrix to start off with. Now the thing is, right now, so far, we have the coordinate frame that is centered at the origin. We haven't done anything with the position of the camera yet. But also, if we were to multiply the world by this matrix that we have so far, this is going in the same direction as the camera, so that wouldn't look right. We need to get the reverse of that. And to do that, we get the transpose of this matrix. So view.transpose. So view is equal to GLM transpose of the view. Yep. And now we also want the position. The position would be negated. The camera's position negated, right? Because we want to go in the reverse direction. And to do that, we can do view times equals GLM translate mat4. So the identity matrix, and get the cam's the negated camera position. All right, and then all we have to do is return the view. That's how we calculate the view matrix. Okay, so that's get view, but to actually see this in action, we need to be able to update the camera's position based on user input. So that's why we're going to need the update camera function, which will be called every frame so that we can update the cam's position. How do we do that? So on the spec, well, on the README in the chute, it said to use the WASD keys so that if you press W, that would move the camera in the direction of the front vector, and S would move in the opposite direction, and A and D would move left and right, so in the direction of the right axis, or the right axis negated. So we need to say we have a bunch of if conditions to check if a particular key is pressed. So glff w get key, pass in the window and glfw key W to get forwards. If we're pressing W, that means that will be equal to glfw press. And inside, we want to go forwards in the front vector. So we want to move in the direction of cam.front. We also want to multiply that by some step. So we need to calculate what the step is. Step is just how our speed, basically. Our speed, we can have a default, like a constant camera speed or something. We can define that up here. Float, constant float camera speed. Let's say that's equal to 5. The thing is, because this is called every frame, this on my computer, if my computer is 30 FPS, then you'll find that I'll be moving really fast. Sorry, moving like half as fast as someone who's running at 60 FPS, which makes sense because this is called every frame. So you can multiply that by the delta time. The delta time being the difference between the current frame and the last frame. So if I'm running at 30 FPS, then the delta time would be larger for me than for someone with 60 FPS. Since it's larger for me, then I'll be technically moving faster, but it's not really, it's just that my frames are slower. It's just to balance it out. So multiply that by the steps. That's the direction I want. That's the direction and magnitude I want to go in front, and then do cam.position plus equals to this. So it'll be very similar for the rest of these. W, A, S, and E. So if I'm pressing S, I want to go backwards. If I'm pressing A, I want to go to the left. So I want to go if I have a right vector, then I can say minus the step. But I don't have a right vector. So let's calculate that. And that's basically exactly the same calculation as this. Let's copy that. So this is the right. And we pass in the minus cam dot front. That's the same as the Z thing we had here, the Z vector here. So that'll be right times minus the step, and this would be just right times the step. Now let's do a little bit more. It's easier for the controls if I also define the up direction, so I can go up and down as well. That would be Z, which is minus cam dot front, and X, which is the one I just got. So up, I can go up if I press the R button, and go down if I press the F button. That's what I want. So let's do that. R and F. Go up if R is pressed, and go down if F is pressed. Okay. So let's actually use this code. Let's go to main and let's first of all make the camera. So static called camera T. Let's call it cam, make camera. So we pass in the position. Let's initially set the position to be like a little bit backwards away from the cube. So that would be in a positive, that would have a positive Z coordinate, and that would be glm vec3 let's say 0.01, and also it would have a target of glm vec3 000. So this means we're looking at the origin from somewhere down the z-axis, 1 unit down the z-axis. Let me make this a bit bigger. Okay. And this means that we can replace this identity matrix here with the view. So we can get the view passing the camp. And also we want to update the camera's position. So we can do that before we set the cam. It actually doesn't matter too much. How do we do that? Update camera. Pass in the cam, the window, and DT. So DT is already calculated for us. It's already in the boilerplate code. And let's give that a run. Hopefully, see if that works. Okay, so we get the same thing, but let me press S. Okay, and at some point it disappears. When I press W and changes color for a bit. So now I'm seeing like the back face. And then I press more forwards and it disappears again. So why is that happening? So looking at this diagram here, whatever is inside the NDC, that is this cube, is what we see on the screen. Whenever our cube moves outside this NDC box, this box from -1 to 1 in the X, Y, and Z directions, whenever it moves outside, we don't see anything. Everything gets clipped off. So that's what's happening. To fix that issue, we can use a projection matrix. And a projection matrix is visually a frustum. And this frustum is a square pyramid with its tip chopped off. And basically our eye position is at the tip of this square pyramid. And whatever's inside the frustum is what we see on the screen. This frustum has a near plane and a far plane. That's just the top and the bottom. And the effect of the frustum is that it maps whatever's in the frustum to the near plane. So maps things to a 2D plane. Okay, but that's also not really the case. It maps things into the NDC cube. So you might be asking, why must we map things to a cube and not a 2D plane? Because we actually just have we actually just see things in 2D eventually, right? Everything's a 2D array of pixels. So what's the reason we have a cube instead of a 2D plane, just the near plane, that is? And the reason is to retain some of the depth information so that we know what fragments are in front of other fragments, so we can discard some of the ones behind. So to define the projection matrix, to get everything inside the frustum to be inside NDC, we can use a GLM function called GLM perspective. And we're not going through the math of this, but essentially it takes in the field of view, and that's normally 60 degrees. But it takes it in as radians, so let's do that. What else do we need? So the aspect ratio. Okay, so you remember from the beginning where our cube was actually a rectangle, or a rectangular prism. Our aspect ratio will basically change the frustum so that the near plane and the far plane has the same aspect ratio as your window, if you specify the aspect ratio to be the same, of course. And that would fix it for you, the scaling issue. So to do that, we can say the width divided by the height. Need more space. Okay, and then we define how close the near plane is to the eye position and how far away the far plane is from the eye position. So in the near plane, we can say that's 0.1. So it is good to have that close to you, so that if you've ever in a game and you go and walk up against a wall or something, you don't see the wall, as you don't see through the wall. If that wall suddenly becomes in the space between the eye position and the near plane, then it's not in the NDC anymore when it gets mapped. So that will disappear. And then the far plane, 20. Let's make that a big number. It may be 50. Doesn't really matter. And let's GLM, so that returns a GLM at 4. Let's call it proj for projection. And looks like I need to make this a double to get it to work. I just can't see the whole thing. Then all I have to do is pass in projection times to get the view. Why is it projection times the view? We want to make sure that we've applied all transformations. So the local transformation of your model, or the world transformation to your models, and the view transformation to your models before. So all the transformations should happen before you do your projection. That's why we define the projection first, because whatever's defined first was actually multiplied by the point last. So let's give that a go. Okay, now I'm going to move backwards, and it gets smaller as we move backwards. That's the effect of the projection matrix, is that further away things get smaller. Now it looks a little bit strange, because don't we expect the interpolation to be smoother than this? Yes, it should. The thing we're seeing here is we're actually seeing things that are behind the front face. So we're seeing some artifacts that come from behind other fragments. So we haven't turned on the depth testing. So this is the reason why that's happening. And if I move to the right, I see the right of the cube just fine. And I can go up and down. Okay, let's turn on depth information. So enable depth testing. So it's GL enable GL depth test. You can find out more information in the docs. So Zeal, I recommend you download this. So if you type in GL enable enables or disables server-side GL capabilities. And we see that there is a depth test. If enabled, do depth comparison and update the depth buffer. Okay, so let's run that. And now we see it's a smooth interpolation because we don't see things behind the front face. Okay, it's looking good. Let's do one more thing. We can let's implement this on mouse move, so that if I move my mouse upwards, it also tilts the camera upwards. And if I move my mouse to the right, it would move the camera to the right. I mean, angle the camera towards the right. To do that, in OpenGL, they use in Learn OpenGL, they use pitch raw, but we can actually get away with not using pitch and raw because that's kind of unintuitive to me, at least. We can get away with using the right and up vectors that we calculated for the camera's coordinate frame. So let's just copy that across. The thing is here, we don't have the access to the camera because this is going to be used as a callback. So let's just get it from glfw get user window user pointer as a little trick to get it. So we'll get the pointer, a void pointer, I think, and we want to cast that to camera pointer, camera struct. Now we have access to it, but then since it's a pointer, we need to say a stab instead of a dot. We need to stab it. Okay, so now we have the right and up. Now, to get the camera to tilt up, if we move our mouse up, we need to record the offset of our mouse movement from the previous frame. To do that, we need access to the X and Y from the previous frame. And we could do that neatly using static variables. So static variables you can think of as global variables that have limited scope, and that scope would just be within this function that you define it in. So static float previous X equal to X. Static float previous Y is equal to Y. And the first time this function is called, these static variables are called and set, but subsequent calls, these would be ignored. So that's a good way to get the previous values. But make sure at the end we actually set previous X to be X, to be the current X, previous Y to be the current Y after we finish using them. But we can get the offset from these now. So the offset would just be X minus the previous of X. Let's call that float dx. Delta X or difference in X, either way works. Float dy. Now we could do Y minus the previous of Y, but the thing is, window coordinates are given to you from your perspective from 0, 0 to screen width, screen height. 0, 0 to screen width, screen height. So that means the Y direction is going from top to bottom, whereas GLFW's NDC coordinates are going from bottom to top. So they're reversed. We need to make sure we negate this or just subtract them the other way around. That would work. We also need to multiply this by some sensitivity value. And it'll be kind of arbitrary. Just I kind of played around with this earlier, and this seems to work well. Now we use dx and dy to add to the front vector of the camera. So the front vector of the camera camera stab front, we can plus equals to the, if we want to go upwards, then we go up times the dy. Cam's front would be would also be the right times the dx as well. So in Learn OpenGL, they did it using some extra variables in the cam struct, using using raw and pitch, as we see in this variable in this image, pitch and yaw. And we have this roll. These are your Euler angles. And this roll as well we ignore because normally you don't want to tilt the camera sideways, but sometimes you do. In this case, we don't really care. this is equivalent way of doing it. I think there is a little bit of difference. One of the other tutors said, but I couldn't really find the difference. So yeah, and then we want to normalize that as well. So front is equal to GLM. We always want to make sure the front vector is normalized. GLM normalize cam front. Now to use this, we go to the main file. The main file, you have to call update. No, we have to, it's a callback. So I need to register with glfw by doing glfw set window, set cursor position callback window, and also the callback, which is on mouse move. But this mouse move expects there to be something in the window user pointer. So I need to set that before window user pointer. Takes in the window and the pointer, which is the position of the camera. Okay, hopefully you're with me. Let's give that a run. Let's go back a little bit. I'm going to move my mouse around, and there we go. I can move up and down. The thing is, when I move my mouse like outside of the window, it stops. Obviously, it stops the callback, so that's not good. It's a little bit difficult to use. So the one way to deal with that is to glfw set input mode of the window to be, oh, it will be glfw cursor, I think, glfw cursor, glfw disable, cursor disable. So we disable the cursor. I think in the glfw docs they mentioned something like this. But basically, it's enables infinite mouse movement without it going out of screen and stop the input, stop the callback from being called. So let's run that. Okay, so now I can move freely and go around the cube. If I go under the cube and kind of keep going under the cube, kind of like limbo, we get some kind of strange behavior. Kind of spazzes out a little bit. Why does that happen? Does anyone have any idea? I'm under the cube right now. I'm looking directly up. Yeah, I think so. One of the tutors corrected me. It said it's not really to do with gimbal locking, he said. And then I was like, isn't gimbal locking because the direction the camera is facing is really up, but then we're using the up y-axis as to cross product with. So then it's getting difficult for the cross product to know what's orthogonal to both if they're very similar vectors. And so the right vector is kind of going all over the place. He said, yeah, that's the issue. But he said that's not really gimbal locking. So I need to look that up. Yeah, but that was the issue. Oh, and we go inside the camera. Sorry, go inside the cube and we see inside the cube. But that kind of contradicts with what I was saying before with the winding order and all that. Where is the winding order? The winding order optimizes the application, I guess, the shader pipeline by throwing away almost half of the, well, up to like, yeah, maybe more than half of the fragments, because most of the time, from our perspective, a lot of fragments shouldn't be seen. And that's if the triangles are clockwise from our perspective. But yeah, so we just have to turn that on, basically. It will be GL enable, GL cull face. So if you turn that on, now let's go inside the cube, and it disappears. We don't see inside the cube anymore. It's because everything inside the cube would, from our perspective, be defined in clockwise order, so they will be invisible to us. But if we go around, we can see it, of course. So let me know if you have any questions. To do with anything I just did. We have a minute left. Oh, one other thing I forgot to mention was all this code here. You can, and I recommend trying to understand this. It's not too difficult. Hopefully my explanation was good enough. But you don't actually need to. Oh yeah, you do. So there is a link in the Discord I sent. If you go, there's a solution branch to that as well. But for this, we actually don't need all of this code. We can just use a GLM function called lookat. But it's like, why would you do this? Because it helped us understand how to get the X and the Y axes. So then we can figure out how to do these and this. So yeah, so we can use this abstracted away using this, but yeah, it's like why. GLM look at eye. So the eye would, I guess, be the camera's position, and then the center would be yeah, no worries. Center would be, well, this one would be the camera, the position plus the center. I think if that's referring to where a point in space where the camera is directly looking at, so it would be camera the position plus camera front, and up is GLM vec3 010, the one we've been using. That should do the same thing. So let's run that. Yeah, does the exact same thing. Okay, so that's it. Hopefully you guys you're on track with the assignment. I think that's due soon, if not rather than later. I don't know. Yeah, tomorrow 5 p.m. Okay. And I'll make sure this recording is available to you. I just need to cut out the first bit. Okay, see you guys next week.